A systematic process for increasing physical asset reliability eludes many maintenance departments.
How can we increase equipment reliability? By capturing and then analyzing maintenance and repair history. Reliability improvement depends on your having performed reliability analysis.
And reliability analysis requires adequately captured historical maintenance event data in conjunction with monitored condition data, such as sensor data, oil debris data, and other observed data sources relevant to an asset's health.
What do we mean by historical event data? Well, two types of equipment history can be recorded and tracked: descriptive and quantitative. Maintenance engineers typically analyze descriptive history, consisting of textual narratives, sketches, and photographs that document operational problems encountered and proposed solutions. A subject matter expert reviews this information and then proposes engineering modifications that will resolve the issue. Maintenance engineers are less familiar with the second type of historical record, required for quantitative analysis.
This type of analysis, called reliability analysis, is seldom performed successfully in the maintenance organization. Why? The primary reason for the paucity of quantitative analysis in maintenance is well known. The history of object parts and their ending events were not recorded with sufficient precision, completeness, and accuracy in the Enterprise Asset Management, or EAM, system database. In this video, we'll look at a new type of data entry form that can fill the reliability gap. It will ensure the transfer of analysis-grade data suitable for reliability analysis into the maintenance historical database. The largely untraveled road to condition-based maintenance optimization depends on correlating failure mode history with condition monitoring data. This multi-dimensional analysis of age and condition monitored data leading to asset performance allows us to answer important questions such as:
what is the actual predictive capability of a particular set of monitored data? What are the monitored variables that are most influential to the probability of failure in an upcoming calendar or age period? What is the probabilistic relationship between those variables and an item's remaining useful life? What is the confidence with which a predictive decision is taken? What is the return on investment of a given predictive maintenance strategy? How can predictive performance be measured?
Predictive performance can be assessed by plotting the conditional probability density distribution. It is similar to the well-known probability density function, except that the origin is not positioned at age 0, when the item was new. Rather, it is located at the current moment in time, which is, of course, the moment at which a predictive decision must be made.
The quality of that decision is measured in terms of confidence, as reflected by the narrowness of the curve's variability about the mean. The mean, by definition, is the object part's remaining useful life estimate, or RULE. Reporting the coefficient of variation, sigma divided by mu, the standard deviation divided by the mean, is a convenient way of tracking confidence in predictive decisions. The equation for this curve is known as the Cox Proportional Hazard Model, or PHM. It predicts the conditional failure probability, or hazard, in terms of the item's current age t and the current values of the significant condition indicators represented by the vector product of gamma and z. The shape parameter, beta, is a measure of the quality with which failure modes and their life-ending events, either functional failure, potential failure, or suspension, have been recorded by the technician. A suspension is the preventive renewal of an object part that has not failed. Successful quantitative reliability analysis for predictive maintenance depends almost entirely on the reporting skills of the technicians. How can we ensure that they record these events accurately? Here is a sample data entry form that can assist in the development of such essential failure mode event reporting skills. The form ensures the quality of data needed for the continuous improvement process. The pane on the left contains the asset RCM tree view. The leaves represent failure modes that can affect asset performance. When a leaf node is selected in the tree view, the corresponding failure mitigating strategy will appear in the center pane. This is key because the technician assures himself, in the light of the revealed object part, object damage, failure effects, and strategy, that the selected node precisely represents the failure mode he has observed and whose occurrence he wants to accurately record. He does so in the rightmost frame. That pane requires selection of an ending event corresponding to each object part renewed during work order execution. The ending event, one of functional failure, potential failure, or suspension, is prerequisite for subsequent reliability analysis. Analysis requires precision in the selection of object part and its life-ending event as one of potential failure, functional failure, or suspension. The good news is that errors can be avoided given the completeness of the contextual information provided in the form's central pane. The form has one more essential feature. Continuous update of the maintenance strategy itself may be routinely accomplished by considering a technician's on-the-spot observations. Text input areas in the feedback pane adjacent to each text box in the strategy pane encourage the technician to suggest changes or additions to any of the strategic information, such as object part, object damage, effects, consequences, and mitigation, in the light of his actual observations. Such valuable information, structured in an RCM-like way, drives incremental strategy improvement so that the maintenance plan can respond better and better to observed reality. A generally recognized management principle suggests that motivation increases when employees, such as operators and technicians, can contribute directly to the maintenance strategy. Declaring a failure mode's life-ending event can be challenging. Operational context is a decisive factor when recording the event as one of potential failure, PF, or functional failure, FF. Fortunately, when completing the form's third pane, the relevant facts are fresh. Discussion among engineers, supervisors, and technicians will naturally evolve into standards for the consistent identification and capture of the ending event. For example, when a certain function, say to contain, has been lost, this by definition would be reported as a failure when leakage rate exceeds a certain standard. But should we record it as a potential failure or a functional failure? The function might be backed up, and consistent with the equipment's strategy, the consequences of the protected function's failure may have been minimal. We might, in such a case, record the event as a potential failure, so as to indicate that our maintenance strategy has avoided the direst consequences of the failure. The identical seal failure, in some other context, could be a functional failure if significant operational, maintenance, safety, or hidden consequences were incurred. Declaring a failure as functional or potential is context-dependent. The form allows us to update the equipment's effects analysis to reflect all reasonably likely circumstances that could arise as a result of this failure mode. If the object part still has an indefinite amount of life remaining in it, but is nevertheless replaced preventively, its life-ending event should be reported as a suspension. A final important point to make is that this reliability-enabling data entry form can be implemented easily using tools and methods already available in your Microsoft Office toolset. Quantitative reliability analysis requires that we enforce a one-to-one relationship between catalog profile object parts and the failure modes identified in the RCM-derived strategy. Here's an example where two object parts were pinpointed in the initial RCM analysis and stored in the Asset Performance Management System, or APMS. But the Enterprise Asset Management Catalog lists from which technicians must make their selections contain far more detail. Those profiles reflect the original equipment manufacturer's engineering design, maintenance manuals, and bills of material. When developing the catalog profiles, erring on the side of greater depth and more detail was considered cautious and thus desirable. However, when setting up the catalog profiles, scant attention was paid to the complexity of matching real situations encountered in the field to long lists of selection choices. The equipment strategy, on the other hand, was built with the benefit of subject matter expert and frontline experience using a structured RCM or similar process that addressed the reasonably likely failure modes, their effects, and consequences. Discrepancies in detail and depth, such as those in these two unrelated lists, given their separate development processes, are not surprising. The technician should not be required to parse long lists of internal object parts that are irrelevant to the maintenance activities performed in actual practice on an asset. In other words, the level of detail imposed by the catalog profiles often contradicts maintenance objectives for the asset in its operating context. When the technician encounters such circumstances, he may use the text areas on this living RCM form to propose the elimination of extraneous detail. For example, often we don't know and don't even care to know precisely
which of the internal object parts listed in the catalog profile was responsible for the failure. It's just not worth it. We simply discard the entire component and replace it with a new item. In such cases, the technician may propose that the item itself be reassigned as the object part whose life ends for whatever internal reason. The sole purpose of captured maintenance event history, specifically the renewal of object parts, is to provide reliability engineers with the ability to perform reliability analysis on a sample of data. A sample is bounded within a calendar window. Data points are the lifetimes of failure modes occurring entirely or partially within that window. The lifetimes included in a sample are represented by arcs. Each arc connects two events, a beginning event, B, with an ending event, by failure, EF, or an ending by suspension, ES. Reliability analysis, in its basic sense, is the counting of the arcs in the sample. Each failure mode's age and its life-ending event will have been recorded in the maintenance history capture process. The dashed arcs represent suspended lifetimes, that is, lifetimes that occur partially outside the sample window. Suspended data contributes to the uncertainty of an analysis. Reliability analysis software algorithms manage the uncertainty associated with suspensions so that confidence in a decision can be stated and thereby considered by stakeholders. The Enterprise Asset Management System can track an asset's working age in calendar or in operational hours, or in any other units considered to be proportional to the accumulated stress on the asset, for example, throughput or energy consumed. Reliability analysis software calculates the age of a given failure mode, that is an object part, at the moment of each event in order to develop a predictive relationship. Unlike the living RCM form, conventional enterprise asset management work order procedures do not explicitly record life-ending events. Reliability engineers, consequently, cannot develop policies based on quantitative reliability analysis with the degree of confidence necessary for their adoption in an asset performance strategy. At best, a suspension is often assumed to be a failure. Such an assumption results in low confidence and overly pessimistic analysis. Now that we have a method to record accurately an object part's ending events, we'll perform reliability analysis on a sample of that data. Consider a fleet of haul trucks subject to the RCM listed failure mode, transmission fails. We'll define the object part as the transmission itself. In other words, we'll not concern ourselves with exactly which internal part failed. There's no right or wrong level of analysis. In some other context, we might have focused on the failure of a particular gear, bearing, or seal, in which case they would have been defined as the object parts. We'll apply a multivariate reliability analysis method to object part events and to condition monitoring data, both occurring in the same sample window. The method is known as exact condition-based maintenance optimization, developed at the University of Toronto by Professors Andrew Jardine and Dragan Banjovic. Within the exact application, our sample appears in a table that combines condition monitoring and event history in a single virtual
data structure. The life-ending events, sorted chronologically, are represented by the symbols EF for ending by failure and ES for ending by suspension. We'll run the proportional hazard algorithm that will parse each record. It will incrementally build a probabilistic model or equation relating the object part's age and monitored condition data to its probability of failure or hazard H. The proportional hazard analysis result displays in a report. Multidimensional regression has converged to estimated values of the parameters beta, eta, and gamma in the equation for hazard rate. The most influential condition indicators were found by statistical testing to be the parts per million of iron and lead. Next, we invoke a transition probability model to predict the transition rates of these significant condition indicators from one range of values to another. A failure probability estimate of failure in the next observation interval is determined for each condition indicator range. This may be observed in a transition probabilities matrix. A conditional probability density graph reveals the object part's remaining useful life, standard deviation, and confidence interval. This video revealed a new quantitative dimension that we can apply to the challenge of equipment reliability. We identified inaccurate event data in the conventional work order data entry process as being the principal structural impediment to reliability improvement. We proposed a living RCM data entry form based entirely on MS Office tools and integrated with the existing enterprise asset management reporting process that resolves the event data inadequacy problem. Finally, we demonstrated the proportional hazard modeling method with which to optimize predictive performance of existing condition-based maintenance initiatives. Thank you.